Welcome to Ziezo tool demonstration. In this video, I'm going to walk you through the different functionalities and use cases of Ziezo tool. Ziezo tool has been developed in Eindhoven University of Technology. The tool aims to support the glass manufacturing and consultancy firm of Pilkington as the main user of the tool, with decisions on the performance of Ziezo window system, on daylight and energy performance in a typical European office model. This is adapted to the dynamic climatic conditions of Eindhoven in the Netherlands, with different window sizes and orientations. The interface allows the user to compose Ziezo window and select the day and time on which they want to preview the performance. Then the tool builds the window from these parts. It gives the user an access to different simulation outputs, consolidate the key performance indicators for daylight and energy, based on pre-simulated cases. In the daylight module, you will see the annual daylight availability that's admitted through the window to the inside, from a static daylight metric such as the daylight factor, to a dynamic daylight metric of the useful daylight illuminance. The center plot shows a point-in-time illuminance levels of 11 sensors, placed on a workplane level of plus 75 centimeters above floor, and distributed across the depth of the office. This module also computes the uniformity of light, which shows how evenly the light is distributed throughout the room. The solar radiation module shows direct normal and global horizontal irradiances, along with annual plots showing daily radiation profiles of a typical meteorological data of Eindhoven. Moreover, it also shows the bifacial boosting factor and total energy generation. In the energy module, you'll find annual energy use intensity and monthly energy plots. Alongside the performance on the room level, the tool also shows the optical and thermal performance on the window level. The Window Analytics module shows the visible light transmittance, U value and G value of the composed window system. On the right side, the feedback panel provides the user with characteristics of the composed parts, performance highlights and insights into when and how often the composed window will admit daylight in the comfortable range. With the input panel located on the left-hand side, simulation results appear in the center, while the feedback panel is shown on the right-hand side. The first use case composes a single Ziezo window, south-oriented, with a window-to-wall ratio of 30%, with no shading and with bifacial solar cells covering half of the window's area. The illuminance on 28th of September at 14 o'clock is very high nearby the window, indicating a high probability of glare and discomfort. The second use case compares a south-facing window versus a west-facing window. As the user navigates through the hours of the day, we see that illuminance levels nearby the west window significantly increases after noon. As sun moves from south to west, the west-facing window emits higher levels of light than the south-facing window. The third use case differentiates between a shaded and unshaded windows. The shaded window uses a curved Venetian blind, with high diffused reflectance set in a horizontal position. With no shading, the window emits very high levels of light compared to the shaded window. The higher levels of light in the unshaded window can be explained by and correlated with the highest solar radiation profiles on that day, as shown in the radiation plot. Meanwhile, the lower levels of illuminance admitted through the shaded window in January are correlated with lower solar radiations. This is due to a fully overcast sky blocking direct sunlight, leading to reducing indoor light to fall below the lighting minimum requirement of 500 lux in an office room. Another observation, as daylighting levels increase, the reliance on electric lighting decreases, which in turn reduces the monthly electricity loads and the annual total energy consumption. The fourth function in the tool is to answer the question, when would be the best time of year to use your window? How many hours per year does your window provide daylight within the comfortable range between 300 and 3000 lux for an office space? And on which days and at what times does this happen? By clicking Generate, the tool performs a basic data analysis on the data to present you with the results. In this example, the unshaded window admits daylight in the optimum range for 229 hours per year. What if we would like to explore the performance further? The user can use this output from the tool as an input for the next evaluation to explore the performance further of any individual case by case in an iterative loop. What will be the daylighting levels on the 22nd of March at 12 o'clock? The user would like to verify the daylight levels at this moment on the 22nd of March. And indeed, the tool confirms that daylighting levels did not fall below 300 lux, nor exceed 3000 lux, on all sensors across the room. This can be a valuable input when designing a shading control strategy. Furthermore, the tool shows the performance at representative dates and times throughout the year, such as summer solstice or spring equinox. The tool allows the user to compose up to 2 windows simultaneously, either to show the performance of a single window or to compare the performance of 2 windows side by side. The tool aims to be informative. As you place the cursor over text labels that begin with an underscore, the tool will provide you with more detailed information about the used metric. What is the definition and meaning of this metric? How was it computed? And what are the minimum requirements for this metric in building standards? The bibliography includes references to standards, parameters, and boundary conditions of the model. Thank you for watching.